Hello and welcome to the continuation of this course for the finite volume method in C++. And in this particular video, we'll be continuing the U momentum equation and hopefully implementing the solve method. And before that, from the last video lesson, we actually implemented the boundary conditions, the assembling of the equation and the under relaxation. So just to recap that, we are going to have a look. So the AP matrix is simply a negative summation of AE, AW, AS, AN, and a positive summation of APU to that value. And the source is the source initial plus the source boundary, where the source initial is the source arising from the convection and from the pressure gradient term. Okay, and the under relaxation for the AP matrix means we simply multiply it by the reciprocal of the under relaxation factor, and the source under relaxation. In order to do that, we take the source final and then add 1 minus URF multiplied to AP multiplied to the U velocity for the U momentum and V velocity for the V momentum equation. And also we have a new variable called RAP rep, which is simply the reciprocal of AP. So you just use 1 over that AP matrix to get the rep. And in the last video, I actually forgot to initialize rep to end APU. So rep and APU are at F matrix size 0, the same size as the ones we have done before. So just make sure that all these matrices are initialized to the same sizes. Okay, so now I have copied a print matrix from the fields class. Let me just pull up workspace pane again. And in the print matrix, I have changed this vec that appears here to U because we want a definitive matrix there. So I'm going to print from I equals 0 to I is U size, which is the number of rows, and then j equals 0 to j is less than ui size, which is the number of columns at every row. And now I'm going to print the AP matrix which arises due to the U equation. Okay, so see, this is the central coefficient matrix, and I'm just gonna comment this guy here and then build and run the project. Right, control, press the keyboard. U equation, relax, build and run. Okay, so this is what we have. At the boundaries in east and west side we have 0.00375, and at the north and south we have 0.00625. So boundary and neighbor values are being modified due to boundary conditions. And let's check the source term. So in order to access the source term, we need to write, and we can actually check from U equation as well. So let's try to see what does the U equation have that we can bring to the main file. So we can print the boundary source just to check if the boundary source is correct. Okay, so as you can see on the north boundary, where the value was 1.0 for the U velocity, it results in 0.002 source value just adjacent to those cells. So this is the boundary source coefficient matrix. Okay, so that will be the only kind of source in this first iteration, because the mass fluxes are 0 and the pressure gradient, because pressure is 0, the pressure gradient is simply 0. So the only source that arises in this equation for the first iteration is coming from the boundary. Right, so now we can actually go ahead and write the solve function using the SIP method. So as I have said here, the solver for the SIP method. So let's go to the equation class and we will write the solve function. Okay, so until now all these functions have been void functions, and this time we are going to write a function that will return a vector field instead of void. So fields, vector field, and we'll call this function solve. It will take a vector field by reference, and it will take a finite matrix, finite met, which is going to be the source term, and we'll take an object of the class solution and an integer, and we will come to discuss what that integer is. So let's go and copy this function to the equation class and say that it belongs to the equation class. So equation scope resolution operator. So now we need to give some names to these vector fields. So I'm going to call the one that we are going to solve for as phi, and this function as source, and solution object as sol, and integer as iterations. Okay, and then we will delete this semicolon, put curly brackets, and start writing the function. So as you know by now, non-void function has to always return something. So we are going to return a vector field, and the vector field will be called phi temp, and it will be initialized to the same number of rows as phi, which is the one we take for reference. In the case of u momentum equation, it will be the u velocity. So phi dot size, and then number of columns will be vector of fields phi 0 dot size. Okay, so we go, and in the SIP method, as referenced in the computational methods of fluid dynamics book, we first have to calculate coefficients of upper and lower triangulation matrices. Okay, so we are only going to do this for the internal field. So this time we actually are going to implement this without calling the for all operations. So we are going to write for unsigned integer I equal 1 until I is less than phi dot size minus 1 and I plus plus. And now we are going to access the column, and to do that we write for unsigned integer j equal to 1 and j is less than phi I dot size and minus 1, because we want to only access the internal elements. And then first we calculate LW. So all these matrices have been already initialized. So LWIJ dot value will be equal to the coefficient at west. So AWIJ dot value divided by 1.0 plus bracket solution dot alpha, which is the probably 0.92 multiplied by un I minus 1 j dot value. Okay, so then we calculate ls. So ls will be simply asij dot value divided by, let's copy this part and paste it here and that to ue, and change alpha remains constant, so we don't need to change that part because now it's towards the result side we need to go j minus 1. Okay, and then we calculate a double called p1, and this will simply be sol dot alpha multiplied by lw. So we've already calculated lw, and then this will be multiplied here times un I minus 1 a dot value, right? And then we calculate p2 dot alpha multiplied by, let's copy and paste this and change this to ls and change this to ue. Okay, now we calculate LPR. So LPR is 1 divided by a bracket ap ij dot value plus p1 plus p2 minus lw ij dot value times ue at I minus 1 j dot value minus ls ij dot value times un. Now this time we go j minus 1 dot value. Okay, now we have to calculate un because we haven't calculated un and ue yet. So we calculate un, and un is simply an, which is the coefficient towards the north side, dot value minus p1 times lpr at ij dot value, and then ue is simply ae at any I and any j dot value minus p2 times lpr ij dot value. LU decomposition method. An, let me just put it back here and make it equivalent. Okay, so now we have calculated the coefficients of upper and the lower triangulation matrices LW, LS, P1, P2, LPR, UN, and UE. Okay, so they are dependent on each other. Now we actually go ahead and calculate the residual. So we took an integer called iterations by reference, and therefore we need to initialize a for loop. So let's just write a comment here saying that what this does is that it is calculating the residual and overwriting the residual with an intermediate vector. Okay, so now we go for the for loop from a int equal l int l equal to 0 until l is equal to iterations, which we take in the function definition, and then l plus plus. Okay, so in the equation class we initialize some values called residual, rsm, resol, and equation name. So now we are going to say that this residual at the beginning of every iteration here is equal to 0.0. And now we are going to copy this for loop again because we are going to do for the internal elements. So let's copy that and delete everything inside. So from I equal 1 to minus 1 to j equal 1 to the size minus 1. Okay, so residual is quite easy to calculate. The residual value at any ij is equal to the source that we take in this function definition. So let's call this guy another name. So we are going to call it source input. Okay, so source input. So source input at any ij dot value minus bracket an ij dot value times phi, which is the u velocity for the u momentum equation, phi ij dot value. Actually this should be j plus 1 because we are using an. Okay, so an times phi ij plus 1 dot value minus as, which is the south coefficient, dot value times phi at I. So south is j minus 1, so we go to j minus 1 dot value, and continuing, now we go to the east side. So east is ij dot value times phi at, so each increment in I plus 1, so phi I plus 1 j dot value minus, now we go to the west side, I j dot value, so coefficient towards the west side multiplied by phi at I minus 1 j dot value minus finally the central coefficient, so AP, so let's put this guy in a bracket as well, so API j dot value times phi at I and j, because it's the central coefficient. Okay, so that's the residual vector there, and we can calculate, now we can calculate this residual, which is a double. So the residual will be simply every time this res ij dot value is calculated, it will be added to this, and the added value will be added using an absolute value, so absolute res ij dot value, and then we are going to update, so res I j dot value will be this minus, let's copy this part so we can easily write, so minus ls times, and south should be j minus 1 minus lw times residual at, so west side should be I minus 1, and this will be multiplied with LPR ij value. Right, so we need to put a bracket here and then a bracket here, so that this entire things gets multiplied with LPR, and that's done. Now we have our final part, and let's just write a comment here, and iteration loop. Okay, so before we go to the final part, when we are actually solving this particular equation, we want to update at the runtime, we want to update the residual values so that we know what's the residual, whether it's converging or whether it's diverging, and therefore we will write a small function or a small description saying the double small is equal to 1 if it is the first iteration, if L is equal to 0. So let me just go back here and say at the first iteration L is equal to 0. So If L is equal to 0, then this value which we implemented in the equation class called reso is equal to the residual. So we are storing the first residual, and after that we calculate the RSM, which is the root square mean, will be the residual, which is the first iteration residual, divided by residual, which is the residual for every iteration, divided by reso plus small. So we are comparing the residual of every iteration to the first iteration, and that's how we calculate root square mean. Okay, so we can print some stuff to the solver now. So we say cout, and then equation name, this is a string. For u momentum, we have given this a name here, which is called the u momentum, and we can change this to the equations that we are solving. Okay, so equation name, inner iteration, and print out L, and then print the residual value. So let's just print the residual, and then also we want to print out the root square mean value, just to see how much improvement in convergence is being achieved at the end of every iteration. Okay, so now we have our final part of this solver class, which is called the back substitution and correction of the velocity. Okay, so let's copy this for loop and delete everything that's inside. So let's just delete. Now when you are doing back substitution, you can't go from I equal 1 to I equals to -1. Instead, you need to go actually the opposite of that. So we start from the full size -2, and we go until, so here I is equal to phi dot size -2, and then here we write I is greater than or equal to 1 minus I. So we are actually going in and not an increment kind of loop, but a decrement loop. Okay, so we can just copy this here and say that this will be the j will be phi at I dot size -2. So even if you write phi dot size, it will still be okay, but just in case you have the number of rows and the number of columns are not same, we need this particular j equal phi I dot size -2. And also here we go until j is equal to 1 and minus j. Okay, so the residual is updated in a back substitution, and simply what this means is that from the residual value, the un j dot value times res I j plus 1, which is towards the north side, so un north side residual, and then ue. So if you can guess it, it will be I plus 1 because ue, so east side, so residual at east side dot value. Okay, so let's just delete these empty spaces. And call, finally we update the value of we solve for velocity, or here in this particular case we are calling it phi. So phi is equal to the value of phi plus the updated residual, and that's the solve method using the SIP solver. And at the end of this all these calculations, after the for loop, we need to say that for all phi temp, which is the vector that we declared here, because we said that this particular function will return a field's vector field, a two-dimensional vector field, and we call this vector field phi temp. And as you can see, we haven't done anything for phi temp yet. We updated the value of phi, but now we will copy the value of phi to phi temp. So phi I j dot value, and then finally we return this vector. And let's check for any build errors. See what it says. Right, we have implemented this function twice, so let's just delete that. Then forgotten to close this bracket, build again. Okay, so it says that the absolute was not declared in this scope. That's simply because we haven't included the math library. So just go to the top of the file and include C math. Here we have forgotten to write a value, and okay, so now it has totally built without any errors. So in this video lesson, we implemented the solve function, which is probably the largest function in the class equation, and we have calculated initially the coefficients of upper and lower triangulation matrices. After that, we calculated residual and overwrote it with intermediate residual, and then we update the solver, which is the in the print screen for the command prompt or the window that you have, what the residual for every iteration is and what the root square mean value is. And after that, we used back substitution and correction method to correct the residual and finally update the velocity or whatever field that we have, and then end the iterations, update the phi temp value, which is the matrix that we are going to return, and finally return the matrix. Okay, so that's at the scope of this video. See you in the next one.